All right, stoichiometric calculations, or stoichiometry. Stoichiometry is a chemist's bread and butter, right?
Bread and butter?
Yeah, well, essentially what I'm saying is that's where we get the power or our ability to do the things that we do, to make the calculations from the stoichiometry of the chemical equation. Whoops. So we need to be able to read this. Do you want to translate this? Read this to me in English?
I can do that. I don't know what that stuff is.
This is oxalic acid, H2C2O4.
Okay. So 2 moles of iron plus oxalic, 1 mole of oxalic acid.
All right, now you didn't call this iron plus 3, right? Do you think that's important?
I don't know.
It is, because see over here, it's iron plus 2, right?
Oh, okay. 2 iron plus 3, 2 moles of iron plus 3?
That's right.
1 mole of oxalic acid, 2 moles of water, 2 moles of iron plus 2, 2 moles of carbon dioxide, and 2 moles of H3O plus.
Very good. Do you remember what H3O plus is?
Not really.
Well, H3O plus is, let me get a little more paper here. It is the same as the hydrogen ion. So a different way to express the hydrogen ion, right? So it is, H3O plus is a way to say H plus ion, okay? I prefer the H plus ion. I don't know why people are so infatuated with the H3O plus ion. I understand, clearly H plus ion does not exist in solution by itself, just like the Cl minus ion doesn't exist in solution by itself. It's surrounded by water molecules. H plus ion is also surrounded by water molecules. It's a little bit different, though. In a network of the atoms that are in water molecules, right? So if you had a bunch of water, like so, and here, for example, an H plus ion appears, then the neighboring water molecule will extend its free electrons and reach out and grab it, right, and create a bond there. But at the same time that occurs, this oxygen here will recognize that that hydrogen is losing its electronic attention that it was receiving from the oxygen, right? And will reach out with its lone pairs and grab onto that hydrogen there. And at the same time that that happens, another water molecule elsewhere will be pulling the proton off of there. And so it's not the same proton. It's moving around. It's within this network of water. It could move from one side of the container and be at the other side instantaneously, essentially, right? So this is occurring extremely fast, right? So H3O plus is, in a way, you could say it's counter helpful, because never do you see H3O plus any more frequently than you would see H plus, right? But anyways, that's what we got. All right, so going back to our book here then. This stoichiometry, the chemical equation here, it has its power in the fact that we know the molar ratio of the different reactants and products. You can make stoichiometric statements about other things as well, right? Not just chemical reactions. You can make stoichiometric statements about a compound like Na2CO3, right? If I have 1 mole of Na2CO3, do you know how many moles of sodium I have?
Yeah, that's 2 moles of sodium.
Very good. So that is a stoichiometric relationship there. If I have 1 mole of sodium carbonate, do you know how many moles of ions I have?
Moles of sodium ions?
I didn't say sodium ions. I just meant moles of ions.
Oh, okay, yeah.
What would the answer be if it was just sodium ions?
That would just be 2 again.
That's right, 2 sodium ions. So moles of sodium ions, right? And more stoichiometric statements that we can make. But I want to know moles of ions, because moles of ions relates to the conductivity of solution. So it's often important. So if I put 1 mole of sodium carbonate into water, how many moles of ions would I get?
3 moles of ions.
Very good. 2 of them are sodium ions. 1 is the carbonate ion, but a total of 3 moles of ions, right? Okay, so all of these are stoichiometric statements which, again, give us the power of chemistry. So this oxalic acid, we can perform a titration or a reaction and find out how much of some solution of iron 3, right? That would be our standard. We would know the concentration of the iron 3, and we would find out how much oxalic acid we had by finding out how much iron 3 was consumed. In this, specific example here, it talks about oxalic acid being in rhubarb. Have you ever heard of rhubarb?
Nope, can't say that I have.
It's like a celery, but it's a little bit redder and has lots of green leaves, but it contains a lot of this oxalic acid. Do you know anything more about oxalic acid?
No.
Oxalic acid contributes significantly to kidney stones. You've heard of kidney stones, right?
Yeah, I've never had one though.
They can be painful. They represent usually just as a sore lower back on the sides. People feel like, oh, my back is sore, and they don't relate it to their to kidneys at all. And so when they show up at the hospital, they usually say, I have a really sore back and it's hurting really bad to move and I need some medicine. And then that's usually a sign that it's their kidneys. That's the first time. After that, they'll know, oh man, I have kidney stones, and you try to drink a lot of water. If you just go to the hospital, they're going to put you on an IV. And they have some chemicals now, drugs now, to help break up those kidney stones, but or actually doesn't help break up the kidney stones as much as it helps relax your muscles so they can pass. But yes, very painful. So the determining how much the amount of oxalic acid in a sample of rhubarb, we took a mass of rhubarb and dissolved it, and then used a 0.013 molar solution of iron plus 3. That's our standard. We know its concentration. Here's the volume that was required, and we want to know the weight percent. We want to know how many grams of oxalic acid there were, and then we're going to divide that by the grams of rhubarb, right? Okay, so what do you think? How should we approach this problem?
Well, we want grams of oxalic acid, right?
Very good. So we can write to the right of our equal sign, grams of oxalic acid. Grams of, I'm just going to call it ox. Is that okay? Oxalic acid.
Okay.
So what are we going to start with?
The 10.62 grams of rhubarb?
No, we need something that relates to the oxalic acid. We have our chemical equation here, right? Chemical equation relates oxalic acid to our iron, right?
And we know moles of iron.
Well, they give us molarity of iron, right? So I can use that 0.0130 molar iron, or I shouldn't have written molar, I should try moles for every 1 liter of the iron solution. Right? Can you see that?
Okay.
So what I'm saying is we knew that this moles was going to be on top because we have a molar relationship between the iron and the oxalic acid. Okay?
Okay.
So I can go from moles of iron now to moles of the oxalic acid, right?
Oh yeah, the equation says 1 mole of oxalic acid for every 2 moles of the iron plus 3.
Very good, and I should be more specific there, iron plus 3. 1 to 2, right? Was that it?
Yeah.
Okay, good. So, now that I'm in moles of oxalic acid.
Oh, you can just go to grams.
Very good. Moles of oxalic acid, grams of oxalic acid. I need the molar mass, right? Do you know the molar mass of oxalic acid?
You could just add it all up.
Yep, or you could ask your phone. Molar mass of oxalic acid.
The molar mass of oxalic acid is 90.03 grams per mole.
All right, so the 0.013 divided by 2 times 90, right, should give us our mass of oxalic acid. Should we do that on the calculator?
I can do that.
Okay, good. Why don't you do that and make sure you get the right value. Okay, and after we get that value, what'd you get?
I got 0.02132.
Very good. So 0.02132 grams of oxalic acid.
Yeah.
All right, now we just divide that by the what?
Oh, by the, how much was the total mass of stuff? 10.62 grams of the rhubarb.
Very good. And when we do that, we get multiply by 100 and we get our weight percent oxalic acid. Okay? Excellent. Now, there's another example here which we can use. And in this example, it talks about this chemical, which is called disulfiram. Now, disulfiram is the main ingredient in an interesting medicine, interesting drug called antabuse. Antabuse. Have you heard of antabuse?
No.
Sounds like anti-abuse. It's the medicine that is used to help people stop drinking alcohol. If you take antabuse, the amount of antabuse in your system will react with alcohol, and the result is an unpleasant smell and flavor in your mouth. So it prevents people from wanting to drink alcohol. Okay? Now, if you wanted to determine the amount of antabuse in a pill, for example, make sure that the medicines that were being made were having the right amount, you'd have to develop a chemical reaction that, you might think initially, okay, I'm going to develop a chemical reaction that interacts with the antabuse. You know, think of some chemical, look at the chemical structure here. Okay, how am I going to deal with this? And you could find some way, and I'm sure that a lot of literature has looked into reactions that interact with antabuse. However, the problem is if you do that, then the antabuse itself has a stability, but the more complex the chemical reaction, oftentimes the less stable the standard, right? A good primary standard, that's what we call it, primary standard, is a solution that you can make, put on the shelf, and regardless of, relatively small temperature changes, relatively small humidity changes, regardless of the amount of light that comes in, your solution's concentration will be the same always. You can imagine if I had some solution of my 0.013 molar iron that I used previously, that I made up 3 months ago, put it on the shelf, and it was gradually being reduced by some water, maybe to the +2 ion form, right? That would be a problem, because then I wouldn't have the right concentration. It would require more volume, and my calculation would suggest that there's more oxalic acid in my rhubarb, right? So this is par for the course. This is how analytical chemistry goes. You don't want to, it's okay to think about very complex reactions to identify the concentration of an unknown. But if you can simplify your reactions, for example, by combusting your sample, right? Now, this is a specific example for this compound here, disulfiram. But if you combust disulfiram, then what you'd get is, now do you remember what combustion means?
I'm not sure. I think it means like to burn.
Yep, burning is another euphemism, or not euphemism, but just different way of saying combustion. But essentially, combustion is taking an organic compound. Now, do you know what an organic compound is?
I was in organic chemistry for a couple weeks, but then I dropped it because I wasn't quite ready. I had a big load, so I have a little bit of experience, but not much.
All right. So we want to make sure that we have enough to move forward in the class. So I'm going to draw this chemical here with a little more detail, just a portion of it at least. So each one of these bends in the compound, and we talked a little bit about this in some Gen Chem classes, but each one of these bends represents a carbon, right? Each one of these bends represents a carbon. And if each carbon has to have, do you remember how many bonds it has to have?
Oh, 4.
That's right, each carbon has to have 4 bonds. So I haven't drawn the whole compound here. I'm just drawing a little bit of it. But if there's not 4 bonds shown to it, then it means that what? Do you remember?
Oh yeah, hydrogen.
That's right. It means that there's hydrogen on the outside. And the definition of an organic compound is really a compound that contains mostly carbon and hydrogen. And another indication that there's some chemistry that could occur here is these what we call heteroatoms. Hetero meaning different, and it's different than carbon or hydrogen. So combustion, again, when you talk about combustion, where's my, didn't I start trying? Oh yeah, combustion reaction here. You have carbon and hydrogen, and then you could have some oxygen or sulfur or nitrogen, and the amounts of these, right, A, B, C, doesn't necessarily matter. I mean, it changes your reaction, but if you combust something like this, combine it with oxygen at high temperatures, you're going to get carbon dioxide and water, right? All of the carbon goes with oxygen, all of the hydrogen goes with oxygen, and then you're going to get sulfur combining with oxygen and nitrogen combining with oxygen. Whoops, X. We don't know if it's sulfur dioxide, sulfur trioxide. Usually sulfur dioxide, right? But I mean, you'd have to know specifically, make sure it's okay. But the premise here is that, okay, so we should talk about the oxygen first. The oxygen here, it goes on anywhere here, so you can't really tell by the oxygen or by the specific amount of any given chemical here about how much oxygen you started with. But you can tell by how much carbon dioxide is, how much carbon you started with, by how much water there is, how much hydrogen you started with, by how much sulfur dioxide, how much sulfur you started with, right? And nitrogen. So when you do this, in this example here, they take the SO2 and, like it says here, you bubble into the SO2 hydrogen peroxide, and that makes sulfuric acid, H2SO4. And then it's easy, that sulfuric acid is going to be pretty stable. And you can tell how much there is simply by reacting it with a base like sodium hydroxide. So we take a complex compound, sulfurim, for example, and we simplify it to make the reaction easily performed, right? Easy acid-base reaction here. Okay, so we're going to analyze some disulfirim. We're going to get a 0.4613 gram sample of antabuse, and we want to know how much disulfirim is in there. So what's going to go to the right of our equal sign?
You want to know how much disulfirim?
That's right. What units do we want to use?
Grams of disulfirim?
Okay, grams of disulfirim. Is it okay if I just call it grams of DIS?
That's disulfirim?
Yeah.
Okay.
Now, what am I going to start with?
Well, they say moles of sodium hydroxide. I don't know how that's going to relate to disulfirim.
Good question. We can get moles of sodium hydroxide to relate to moles of H2SO4, right? And we know that the H2SO4 came from the disulfirim.
Yeah, but you don't know the equation of the disulfirim combusting exactly to the sulfur dioxide, or the H2SO4, do you?
That's a good point. And we could figure out that equation. But there's another little trick that we can use. If we just look at the sulfur.
What do you mean?
Well, where did the sulfur come from in the H2SO4?
From the sulfur dioxide.
Okay, and where did the sulfur dioxide come from?
The disulfirim.
That's right, it came from the disulfirim. And I can just use the sulfurs themselves and see that each disulfirim has 4 sulfurs, and each H2SO4, which resulted from the decomposition, the breakdown of the disulfirim, has 1 sulfur. So can you see how that would lead to a conversion factor of 4 H2SO4s need to exist for every 1 disulfirim?
Okay, I see that. Okay. Yeah.
And I could throw in there moles to clarify that a little bit.
All right, so yeah, then we can just go from our sodium hydroxide to H2SO4, and then 4-to-1 to the disulfiram.
Very good. So let's go to the sodium hydroxide here. Where is it at?
0.025.
Okay, 0.025 molar sodium hydroxide. Not molar, should we do moles for every 1 liter, right, of the sodium hydroxide solution. Okay?
Yeah, and then we're going to go moles of sodium hydroxide to moles of H2SO4.
That's right. Moles of moles of sodium hydroxide to moles of H2SO4. Very good.
And that's 2-to-1.
Very good. 2 here to 1 there. Is that right?
Yeah, that's the equation told us.
Excellent. So now I'm in moles of H2SO4. Now where am I going to go?
Did you say 4-to-1 disulfiram?
Very good. So I'm going to go moles of disulfiram, right?
Yeah, okay. And then moles of disulfiram to grams of disulfiram.
Very good. So I'm in grams of disulfiram. Is that it?
Yeah, I think that's it.
There's one more thing that we have to do.
We're not done yet?
Look at your units. Always use this as your roadmap to see your units.
Okay, so moles of sodium hydroxide.
Yeah, moles of sodium hydroxide were canceled out there.
Moles of H2SO4. Moles of disulfiram. Oh, that's a 1-to-4, right?
Yeah, 1 to 4 moles of H2SO4 for every 1 mole of disulfiram.
Oh, the liters of solution.
That's right. We have liters of solution on the bottom. So we got to get rid of those liters of solution. Can we do it on the back door? Is that okay? I could put it over here. It's not a big deal. But if I do it on the back door, it just looks a little bit nicer. Maybe I even do the conversion in my head. So I have 0.03485 liters of the NaOH solution. Is that okay?
Okay, good.
So 0.03485 times the moles of sodium hydroxide divided by 2 divided by 4. Oh, we need to know the grams per mole of disulfiram. What's the molar mass of disulfiram?
The molar mass of disulfiram is 296.54 grams per mole.
Oh, 539 grams per mole. Now, you can see by them giving me 4 significant digits here, 4 significant digits here, 4 significant digits here, that they want their answer in 4 significant digits, right?
Oh, yeah.
So you want to make sure that when you have a new value that you're bringing in, you bring in plenty more than 4 significant digits, right? Does that make sense? And then you just put it in your calculator, and you can, again, almost all the problems that we do are going to have just mainly multiplication and division, and so, well, a lot of them at least. And so finding the significant digits is really straightforward, like we saw here, right? They're going to give you values so that you can see how many significant digits, and the answers are never going to be differing in significant digits, right? So, all right. So let's follow what they did here. They stopped at, they identified the moles of sodium hydroxide, and then went to moles of H2SO4. And then after they got moles of H2SO4, they went to moles of sulfur, and then 4 moles of sulfur for every mole of disulfiram. And then this is how many moles of disulfiram. Oh, we didn't quite finish though, did we? We needed to take that grams of disulfiram and divide by our grams of sample, right?
Oh, yeah.
Okay, so when you divide by the grams of sample times 100 to get your weight percent. Okay, very good. Excellent. So let's move on now to our equipment chapter, basic equipment section, 2.4 here. Okay. Equipment for measuring mass. Well, first let's preface this by saying there's a lot of different equipment out there. A lot of different equipment that can do a lot of stuff. And if you become, or if you major in graduate school in analytical chemistry, it's kind of an odd, that's not odd by any stretch of the imagination, I shouldn't say that, but it's not hard, it's hard to predict what you'll be doing as an analytical chemist. Because a lot of people would say analytical chemists look at the amount of a given toxin in the environment. But a lot of analytical chemists, what they'll spend their time doing is making a new instrument, right? Making a mass spectrometer, for example, making a new NMR, either apparatus, method, something like that, right? So, yeah, there's a lot of equipment out there. Some of it is very specific to what you want to do. But we're going to focus on these early chapters, at least, mostly on in class. In the lab, we're going to try to get involved with the equipment sooner. But in the class, we're going to focus mostly on mass of material and volume of material, and talk a little bit about the drying of materials. Okay? So, to measure mass, we have a balance. And we sometimes, I mean, you'll hear it in the lab everywhere, even me. I'll say, how much does it weigh? What's the weight of something, right? And the terms are generally used, weight and mass are used interchangeably, but they shouldn't be, right? Because weight is different, and we kind of want to make sure we have a good understanding of the difference between weight and mass. So I always ask people, do you lose weight if you go to the moon? What do you think? Do you lose weight if you go to the moon?
No, you don't lose weight.
Well, you don't lose weight, but you do lose, well, you weigh less. So let's explain what we're talking about here. If I am on the Earth, here's the Earth compared to the moon, right? If I stand on a scale, right, and this is another thing, we often use the term scale and balance interchangeably in the lab, which isn't that big of a deal. Maybe some sticklers might get off on, get excited about correcting people and say, oh, that's wrong. But on a scale, generally you stand on a scale and a spring is pressed down because of the gravity, right? And as we see here in this equation, weight is related to not just the mass, but the gravity that you're on. So if you're on the moon, if I have here a mass of 600 pounds on the scale, on the moon it's going to weigh 100 pounds. I guess grams is better. 600 grams going to 100 grams. If I have a balance on the Earth, balance on the scale, and I stand on one side, and if this one is 100 pounds on the Earth, what is it going to be on the moon?
I feel like it's going to be the same.
That's right, it is going to be the same. All right, the same mass on the Earth as on the moon if you're using a balance. And that's because, yes, we have more gravitational pull there, but it's on both sides. We have less here, but it's on both sides the same amount. Okay? So the difference between mass and weight, and the difference between a balance and a scale. If we look at our balance, a typical electronic balance capacity, it's not too high, and sometimes you can run into trouble if you need to have very large masses. But usually that's what you want to avoid. We don't want to have excess material. We want to try to have less material required. And they can measure to the nearest 0.01 milligram or to 0.1 or plus or minus 1 milligram. So it's between 1 to 0.01 milligrams. Now that's pretty small, and there is a definite advantage to creating an assay that measures anything. I mean, if you had an assay that told you whether or not somebody had coronavirus and it relied on ultimately the mass of something, it would be very accurate. It would be very accurate because scales are good at what they do, right? And it doesn't take much skill to put something on the scale. I've had a lot of experiences, times where people would doubt the results that you have, but if you can tie those results back to a scale and say, the assay works like this, and then you just weigh the resulting material. As long as you have everything buttoned up in front of the final step, the mass on the scale is a really way to be accurate and differentiate. Okay, so if a sample is moisture sensitive, you have to be careful. You always want to keep your balance clean, right? You always want to make sure that the materials, the containers that the weigh boat, we call it, that you use is clean. Typically, people will get a new plastic weigh boat. To tare is to allow the balance to come to zero, to place it at zero, right? You can weigh by difference. So I can weigh a sample, perform some chemistry on it, and then come back and weigh the sample again. And that difference can be informative as well. All right, let's move on to, let's talk a little bit about how you would dry a sample. You'd use a desiccator. Have you ever seen or used a desiccator?
I've seen those around, but I've never used one.
All right. There's a lid. The lid is sealed very good with a mineral oil or a mineral gel, or a hydrocarbon gel of some sort, and that inside that space becomes dehydrated because down below you have a desiccant. Calcium chloride is generally what it is, and it will absorb water from your surroundings, from your sample. And so you can dry things inside here. You want to be careful about putting something that's hot in here because that can create pressure and can either break or push the lid off, right? But yeah, there are desiccators available to help us make sure something is dry before we weigh it. Okay. Volumes. To weigh out volumes, we can have a variety of different pieces of glassware. And, people tend to run to the graduated cylinder, whereas the graduated cylinder has a significant degree of inaccuracy. For a 100 milliliter graduated cylinder, for example, it's accurate to plus or minus 1 milliliter. All right? And that's kind of a problem. Have the volumetric pipette. Volumetric pipette, and I think you guys have probably heard the term volumetric before.
Yeah, we used volumetric flasks before.
Very good. So volumetric flasks, right? And volumetric pipettes are similar because they only have one graduate.
Right, just one line.
That's right. If you look at this one, a 10 milliliter graduated, volumetric pipette has an accuracy of plus 0.02 milliliters, right? So here we have an accuracy of plus or minus 1 for a 100 milliliter graduated cylinder, typically plus or minus 1% for whatever the volume is. Here, it would have to be 0.1 to be 1%, right? And so at 0.02, we're 1/5 of that percentage, right? So increased accuracy there with the larger volume here with a smaller neck where the measurement is made. And that's what gives the volumetric flask its accuracy as well. All right. This here is a Molar measuring pipette or just a measuring pipette, a graduated pipette, right? It counts, the graduates on the side can count up from the bottom, so you can measure as you're taking up solution, or you can start with a certain amount and measure how much you've delivered, right? So it starts up here, counting it from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to count how much you've delivered starting from 0. Okay. It's interesting, scientists at the National Laboratory have made a pipette that delivers 35 zeptoliters, 10 to the minus 21 liter drop of a liquid germanium alloy. So, anyway, micropipettes. These are the kinds of micropipettes that we're used to. They come in a variety of volumes, okay? And you need to be aware of what they can and can't do. You want to stay away from the lower ends of any of these volumes. So if I see that I have a micropipette that delivers between 100 and 1,000 microliters, I don't want to stay towards the 100 region, right? That's the lower end. If this one delivers 20 to 2 microliters, 2 microliters on a 20 to 2 microliter micropipette range, right? The 2 microliter range or volume is very low, and so you want to stay away from that volume. Do you remember working with micropipettes at all?
Yeah, we worked with them in a Microlab, or was it a bio, and in Gen Chem.
That's right, we did. We worked with these. And so some of you are more familiar, and if you use them in the future, one of the major things that you have to make sure you do is you have to make sure that you calibrate them. Do you remember how we calibrate them in 105?
No, I guess I don't.
Well, remember we were in the first lab, we were just measuring volumes of water, the mass of volumes of water.
Oh, yeah.
Yeah, because the density of water is 1 gram per milliliter, then you can easily just take a given volume of whatever you're trying to deliver and put it on a container that's on a balance, and you'll be able to see what the actual volume is.
Is that a scale or is that a balance?
Oh, you're going to get technical with me, huh?
Well, I was just wondering.
Typically, something like this, you would think, oh, that's a scale because I don't see the 2 arms. But in fact, inside the mechanism here, there is an additional arm that has a mass. And so this is a balance. But you're right. You can call it a scale or a balance. It's not a big deal.
Oh, that's interesting.
All right, back to this then. So, measuring with the micropipette, you put a bit in some container that's on the balance, and whatever it reads, that is going to be a pretty accurate way of determining that you've delivered your appropriate volume. Now, you don't just want to do that once. You want to do it like 4 or 5 times and take the average, because there's a lot of manual error that can occur, user error that can occur. Okay? All right, volumetric flasks. See their error right there? Well, let's think about this really quick. If, what was I going to say? Oh, yeah, this one here. If I have an error of 0.02 milliliters, if I have an error of 0.02 milliliters for my 10 milliliters here, what mass is that going to be on my scale?
0.02 milliliters?
Yeah.
Well, 1 milliliter is 1 gram, right?
Very good.
So 0.02 milliliters is 0.02 grams.
Okay.
So that's 20 milligrams, or 0.02 grams. Yeah, so 20 milligrams.
Very good. So what we learned there is that a microliter is the same as a microgram. Is that true?
Yeah, a milliliter is a milligram. No, a milliliter is a gram.
Okay, so a milliliter is a gram. So a milligram is a microliter. That's it, right?
Yeah, milligram is a microliter.
Very good. So if I deliver 100 microliters, it should weigh 100 milligrams, or 0.1 grams.
Yeah.
Okay, good. Excellent. All right. On volumetric glassware, pipettes or flasks, you are going to find information along these lines that says 10 milliliters, its volume, TD, which means to deliver. These volumetric flasks are made to, if it says to TD, that means to deliver. And volumetric pipettes are made to deliver. On a volumetric flask, it won't say TD, it'll say TC. What do you think TC stands for?
That cat
No, to what?
to, I don't know.
To contain. So TD is to deliver and TC is to contain. So if I fill up this 500 milliliter volumetric flask, that's going to be very accurate with the the given accuracy, plus or minus 0.02 or 0.1% or whatever it says, but it's only going to be that accurate as far as the solution that's in that container. Once I try to dump this out and put it somewhere else, getting out all 500 milliliters is not something that this volumetric flask will be good at. Okay, so here is where we make a solution that will be a known concentration, but we have to be aware that not all material, not all flat glassware is made to deliver or to contain. So we can't just use it as if it is. Does that make sense?
Yeah.
So if I want 100 milliliters of something and I make 100 milliliters here and then I try to pour it into something else, I'm not going to get all my 100 milliliters out necessarily. Some glassware is newer, some glassware is older. You can treat the inside of glassware with potassium dichromate, and that will oxidize away any oils and try to give you a good cleaning, and then rinse it out really well with water, and then that increases your ability to deliver. And sometimes you'll do that with volumetric glassware. Yeah, pay attention to TC for to contain and TD to deliver. The bottom of the meniscus, right? The bottom of a meniscus. Now, menisci, they occur because the water has an attractive force to the glass, right? It has a adhesion forces. It interacts molecularly with the glassware, and so it climbs up the glass a little bit. So we always measure at the bottom of the meniscus when we have a meniscus going that direction. Now be aware that if you use a tube to measure anything and you have something that's hydrophobic in there, it's likely that you'll have a meniscus going the other way. And then in that case, you're going to want to measure the top of the meniscus. So if you put oil or something hydrophobic into a glass container, you would expect a meniscus like that. If you put something like water or any aqueous solution, you would expect a meniscus like that. Okay, reading at the kind of the top or the bottom of the meniscus, depending on your perspective, right? Okay, so equipment for drying a sample. We have ovens, right? But we're not going to be, we don't use those in labs, but that is something that is available to us. We have our desiccator, as we mentioned. The material down here, often with the calcium carbonate, is some dye, which will change color, either blue or red, to indicate whether it has moisture or not. Pink indicates that your material is wet. Blue indicates that the material is dry. And so if you take this out of the desiccator, put it into a beaker into the oven and let it dry for, usually doesn't take too long, depends on how much heat you have. You can even put it in the microwave and let it kind of heat up like that. It'll gradually drive off the water and turn blue, and then you put it back in here. And then the presence of any blue is usually enough to indicate that your sample is okay. Your sample is going to be dried by that desiccator. It's dry enough. All right, desiccator, desiccant, the material down below here, right? Okay, very good. Now, on to section 2.5, preparing solutions. All right. This is probably, again, one of the things that is most important and that you're going to be doing most actively, right? You're going to have to always prepare solutions. Oftentimes we prepare what's called a stock solution. This is a solution that hopefully it's made of a standard, but not always, but it's going to be of a higher concentration that we can always dip into and pull out for our chemical reactions later. The advantage of this is if I have 20 different chemical reactions that I'm going to be running over the next 2 days, 2 weeks, whatever it is, and I'm always constantly making a new solution, why would that be a problem?
Well, it takes more time.
It takes more time. What else?
I don't know.
Well, if you have to make a solution 10 times as opposed to once, you have 10 times as much chance of, even though it might be low, you still have 10 times the amount of chance of making an error, right? So if you make 2 errors out of the 10 times that you make the solution, then those 2 experiments will look odd, not make sense, right? Okay, very good. So a stock solution can be helpful that way. Let's see. Describe how to prepare the following 3 solutions. 500 milliliters of 0.2 molar sodium hydroxide using sodium hydroxide. Any ideas?
Well, I could calculate it.
Yeah, that's right. That's what we want to do. Should we work on one together?
We did a lot of these in Gen Chem.
Yeah, maybe we should just let you guys kind of review. Maybe we'll do one here, okay?
Okay.
So we want to determine the amount of sodium hydroxide solid necessary to make 500 milliliters of 0.2 molar solution of sodium hydroxide. Okay, so we have to do our calculation first. What goes to the right of our equal sign?
Grams of sodium hydroxide.
Very good. And then I start with what?
Well, so grams relates to moles of sodium hydroxide, so you want to start with the 0.2 molar.
0.2 moles of sodium hydroxide for every 1 liter of solution, like that?
Yeah. And then you can get rid of liters. You're making 0.5 liters.
All right, 0.5 liters. I converted that 500 mils to liters in my head, right?
Yeah.
Okay, 0.5 liters. And so liters of solution is gone. I'm in moles of sodium hydroxide. And I need to go to I need to go to grams of sodium hydroxide. Right? Oops.
Okay, what's the molar mass of sodium hydroxide?
Well, why don't you ask the phone? I think it's 40. What's the molar mass of sodium hydroxide?
I thought I was going to ask.
Sorry.
The molar mass of sodium hydroxide is 40 grams per mole.
40 grams. So 0.2 times our 0.5 times 40 will tell us how many grams I need to get. Very important part. Now what do we do?
Then you get that mass, and then you put it into a 500 milliliter volumetric flask. Volumetric flask, right?
Yes, that's right. The volumetric flask is the one that's going to look like this, correct? Right, our volumetric flask. We put in our mass of sodium hydroxide, and then what?
Then you fill it up with water.
Okay, very good. Now let me talk a little bit about filling a solution up with water. If I fill it up to here, depending on the material, almost always the resulting combination will be less. But sometimes as something dissolves or mixes, the resulting volume can shift upward. Okay, so if you just put in a volume well below the actual mark and then shake it until it's dissolved. And then once it's dissolved, you top it off with just the water. That will decrease the likelihood of an expansion. Does that make sense?
Okay, yeah, I'll do that.
The other thing that you can kind of want to be aware of is when you're weighing out your sodium hydroxide.
What do you mean?
Have you ever weighed out sodium hydroxide before?
I don't think so.
Well, sodium hydroxide is very hygroscopic. Do you know what that means?
Let's see, what was hygroscopic that we were talking about?
I can't remember. Feel like we mentioned the word before.
Oh yeah, the calcium chloride.
Very good. The calcium chloride was absorbing the water. We said that it's hygroscopic, so it takes the water out of the air.
Okay.
Sodium hydroxide is extremely hygroscopic. In fact, it's so hygroscopic that when you put it onto a container, you'll begin to almost see it melting, right? It looks like it just sweats right away. So weighing out your mass of sodium hydroxide quickly is important. And for that reason, making a solution of sodium hydroxide is usually not considered a good primary standard. It would be a secondary standard because after you have your solution, you can store it in a way that's stable or relatively stable, but it's not a very good primary standard. In fact, if your solution of sodium hydroxide is very high and you store it in a glass container, it will etch away at the glass. And that etching is not just removing the silicon into solution, it's reacting with the silicon of the glass and decreasing the concentration of the sodium hydroxide consuming it, right? So you find yourself in a situation where if you store sodium hydroxide in glass at a high concentration, you'll ruin the flask and you'll also, or the glass container, whatever it is, and also won't have a good standard to use later. Also, you want to store sodium hydroxide in something that doesn't, well, that's not as important, but oftentimes standards are stored in opaque containers. So plastic, dark brown containers that will not allow light in. This isn't as important for sodium hydroxide, but these are ways to store standards, okay, or stock solutions. Another perspective on stock solutions that I want to talk about, okay? If I am performing a biochemical reaction, right, where I'm mixing a biochemical like an enzyme or a fragment of DNA with another chemical, then I have to be aware of the extreme fragility of the lifetime of that biochemical. So enzymes, if I have a solution of enzymes, and I just put that on the tabletop, the solution will gradually lose its activity. Or in other words, the enzymes will gradually unfold, denature, become unreactive, right? And if so, we store them in ice, but even the transfer from the fridge to the ice will begin that process of inactivating the enzyme, or in some cases the DNA. DNA is significantly more stable, but anything that's biological has a lifetime, right? So if I make a stock solution of an enzyme, but I don't use up the stock solution, then that means I have to make an enzyme solution every single time, which again increases the chances of making errors.
So what do you do?
Well, what you do is you make a stock solution, but then you aliquot it into lots of different volumes. So for example, I make, usually these are small volumes because enzymes can be expensive things. So I make, a 1 milliliter sample of, maybe it's bovine serum albumin, BSA is the name of a specific protein that's used frequently in assays. And then I get lots of different vials and I put maybe how much I would need for a typical reaction or a little bit more. Maybe that's going to be like 6 microliters or 10 microliters. And then I fill them all up and then I store them in the freezer. And now one more thing about before you store them in the freezer, how you freeze a biological entity is important.
Oh yeah, I remember that.
Oh, do you? Did you take some biochem?
Yeah, I took biochem lab, and we had to use liquid nitrogen to freeze the cells.
That's right. A quick freeze decreases the likelihood of the crystals that form from bursting through biological entities or, causing damage to large biomolecules. Okay, so liquid nitrogen to quick freeze, and then you store them in a minus 30, basically minus 20, sorry, basically a freezer. And in the minus 20, you have your box, and then when you need it, you pull one out at a time, thaw it on ice. So you put it on ice and let it thaw that way. And if you repeat that process every time, then that increases the likelihood of your experiment working the same way every time. Okay, very good. Talking about very important things here. Okay, so how do you prepare the following solution? We talked about that using sodium hydroxide. We talked about the specifics associated with making sure that you take into account the speed. You have to make sure you weigh it fast. You have to make sure you don't store it in something that's glass. Make sure your concentrations aren't too high. 0.2 molar is probably right on the edge of pretty high for interacting with the glass around it. All right, so we have some other examples here which you can go through and try to figure out, and we'll have opportunities to do this thing. I want to talk about a specific example of a problem here. How do I make a 100 part per million copper ion solution? Okay, how do I make a 100 part per million copper ion solution? All right, do you remember what 100 parts per million means?
Parts per million. I'm sorry, I don't remember.
Parts per million. Now, I think it's just easier for us to memorize this. It's going to be 100 milligrams for every 1 liter of solution. 100 milligrams. So this is, I want 100 milligrams of what?
Of copper.
That's right. Milligrams of copper for every what?
You said 1 liter?
That's right. 1 liter of solution. Okay. Now I'm never going to, I might make a liter of it, but generally I'm going to make a much smaller volume. But that's what parts per million means. And maybe I'm going to say, how do I make a 10 milliliter, 100 parts per million copper solution? Okay. Now, what do you think? What would you do?
You mean how much copper would I need?
Yeah, we need to know how much copper would you need?
Well, you need 100 milligrams for 1 liter, and that's 0.01 liter, 10 mils. So you just multiply them, right?
Okay, so you're solving for the milligrams of copper. Is that what you're doing?
Yeah, isn't that right?
That's fine. Yeah, so let's do that. So if I need 100 milligrams for every 1 liter, 100 milligrams of copper for every 1 liter, and I only want 0.01 liters, that's my 10 mils, then this, liters will cancel out, will tell me how many milligrams of copper I need, right? 1, 2, so 1, 2, right? So is that 1 milligram of copper, right?
Okay, yeah.
So now I need to get a milligram of copper. Where am I going to get a milligram of copper?
Can you go to the stock room?
You can go to the stock room, but if you take a gram of copper, that's not going to dissolve into water.
Oh, okay.
And also, we want 1 milligram of copper ion, right?
Oh, okay. How do you get copper ion?
Well, there's a couple ways. You can take some metallic copper and dissolve it in an acid, which will dissolve it, break it down, and result in copper ion. But generally, the way you're going to do this, well, not generally, but, a typical way is to use a salt, something like copper sulfate.
Oh, so you go get a milligram of copper sulfate?
Well, that's what we kind of want to look at here. If I need a milligram of copper ion to make 100 milligrams of copper, 100 part per million copper ion solution, right? And let's say I'm using copper sulfate. And let's say it's a hydrate, because copper sulfate almost always comes as a hydrate of some sort. So we have copper sulfate pentahydrate. So that's the question that we need to know, is how many grams of copper sulfate pentahydrate do we need to get if I want 1 milligram of copper ion?
Oh, well, that's a little tricky. Let's see. Can I relate milligrams of copper to grams of copper sulfate?
Yeah. How would you do it? Milligrams of copper to copper sulfate?
Well, let's see. I know how many moles of copper are in a unit of copper sulfate.
That's good. That's a good recognition. And that's taking advantage of your stoichiometric relationships. I can go from milligrams of copper to grams of copper. And then I can go from grams of copper to moles of copper, right? And then I can go from moles of copper to where?
Moles of copper sulfate.
Very good. Moles of copper sulfate, pentahydrate, right?
Yeah.
And then I can go from moles of copper sulfate, pentahydrate, to grams of copper sulfate, pentahydrate. Okay? Very good. So, I want 1 milligram of copper. There's 1,000 milligrams of copper for every gram. What's the molar mass of copper? That's just how many grams per mole, right? So it's just the molar mass of copper. I'll bring up my periodic table here. 63.546. What's the ratio there?
Use 1 mole of copper for every mole of copper sulfate.
Very good. 1 mole of copper for every mole of copper sulfate. How about this one?
I don't know. Ask your phone.
Okay.
I'll ask it this time.
All right. You go ahead and ask it. It's ready.
Okay. How many moles of copper sulfate are in... Wait, what am I asking?
You're asking what's the molar mass of copper sulfate pentahydrate.
Okay. What's the molar mass of copper sulfate pentahydrate?
The molar mass of copper, 2-sulfate pentahydrate is 249.68 grams per mole.
249.68. Is this copper 2 sulfate? Yeah, it is, huh?
It is. Good. That's a good recognition. Copper 2 sulfate. So we got 249.68 grams for every mole. All right. We're going to do this in the calculator really quick. We got... let's see if we can see the calculator very good. Hold it up above there. There we go. All right, so 1 milligram divided by 1,000, that gets us into grams. Divided by 63.5, 46, times 249.68. Okay, 0.0039. 0.0039. 3929. All right, so that's how many grams of copper sulfate I need to, and what do I need to do with that?
We're making 10 milliliters of 100 parts per million. So that's how much is going to go into 10 milliliters of water, right? Well, fill it up to 10 milliliters.
Very good. So making a solution, right? 10 milliliter volumetric flask is what we'd want to be using. We're going to put this mass into here, fill it up to 10 milliliters with water. Now, would you be able to weigh out 0.0039 grams on the balance?
I think so.
Okay, that's on the lower end though. It's not quite to the complete low end, but it's really close. In fact, I wouldn't really be comfortable weighing out less than 0.001. Right, 0.001 would be the absolute bottom, and I'd prefer to keep it in my tens of milligrams because slight changes on the balance can affect these regions. You know, the tenths and the milligrams and the tenths of a milligram. Okay, so how could we fix that if we wanted to be a little more safe in terms of using our balance?
Make the solution more concentrated, weigh out 10 times as much, and then make it 1,000 parts per million.
That's one way. Very good. That's one way. And then we would have a stock solution that we could use later on. What if I just made 100 milliliters instead of 10 milliliters?
Oh, yeah, you could do that. And then that would be 0.03 grams, 0.0392 grams.
That's right. Very good. Excellent. So, yeah, very important things we're talking about here, making solutions, thinking about how much mass we want to comfortably weigh out on a scale. When we talk about 1,000 parts per million copper, that's not 1,000 parts per million copper sulfate, right? Or sorry, 100 parts per million copper. That's not 100 parts per million copper sulfate. So make sure you have to do your calculations to know how much copper sulfate I'm actually gonna weigh out. Okay, very good. Okay, now we want to talk about preparing solutions by dilution. Okay, now the dilution equation. Do you remember the dilution equation?
I just saw it there for a second, but the dilution equation is like C over V equals C, or V, C1, C, I can't remember exactly.
All right, well, this is definitely something that we want to have a way to remember. And the way isn't to just say, I looked it up, right? Because it's intuitive to us. It's inside of us. We have had experiences where we've had to use the dilution equation. So we want to be able to regurgitate them at any time. And in the process of regurgitating, it kind of solidifies in our mind because we understand it better. All right. So I'm going to talk you through the same experience I talked you through in Chem 105. All right.
About the party?
You remember the party?
Yeah.
And some of you didn't take Chem 105 with me, but tell us, Fred, what about the party?
When you're at a party and the punch is too gross.
What do you mean too gross?
It's too sweet, too strong.
Okay, very good. So if I have punch and I am at the party, what do I know?
You know the party's no good.
Okay, very good. If the punch is too sweet, you know the party is the wrong kind of party and you want to leave. But if you decide not to leave, there are some options available to you. What are the options?
You can dilute the punch.
Very good. I can dilute the punch. If I decide I want the punch to be half as concentrated, what can I do to dilute it? How am I going to dilute it?
You have to add, if you want it half as concentrated?
Yeah. How much water do I have to add?
Oh, you have to add the same amount of water as you have punch.
Okay, very good. So either I'm going to have to get a slightly larger container or pour out some of my punch. But in the end, I'm going to have a volume of solution, which is twice the volume, but half the concentration. Do you see that?
Yeah, I see that.
Okay, good. So our initial concentration, let's give our initial concentration a value. Can you give me a concentration there?
2 molar?
Let's try 5 molar.
5 molar?
Yeah, okay. Good. 2s are kind of scary. All right. What's the final concentration over here?
It's half as much, 2.5.
That's right. Very good. Concentration final. 2.5 molar. What is the initial volume over here?
100 milliliters.
Very good. Whoops. 100 milliliters. Initial volume. What's the final volume over here?
It's going to be 200.
Very good. Now from this, we should be able to regurgitate the relationship between these sets of values. Okay? And, it doesn't really matter what the setup is. C1 V1 equals CF VF is what we find out. But you can rearrange this. You can have it C1 over CF equaling VF over V1, right? And still solve for any one of those if you have the other three, right? So whatever you get, the relationship is what's important. And being able to regurgitate it is even more important, right? So when I want to make a dilution, so here's an example. We need 250 milliliters of 0.1 molar ammonia solution. And how would you prepare this stock solution if you had 14.8 molar ammonia to start off with? Okay? This is pretty straightforward, so I'm not going to go over it here, but not going to go over it on the paper, but our initial concentration times our initial volume, final concentration, final volume. The units here, molarity and molarity, or milliliters and milliliters, they aren't particular. just as long as they're the same on both sides. So you could have parts per million, you could have volume in terms of cups, liters, right? Anything. Okay. So I think that there are some other, here's a problem here. If you want to work through that one and see how they did it, that would be a good idea. All right. So this is a good place to stop for chapter 2. All right, good.